Imagine you are an astronaut on the ultimate dare, drifting through the deep, silent void of space toward the most powerful and extreme object in the universe, a black hole. As you approach, you realize this isn't a hole at all, but a massive concentration of matter packed into a tiny space, creating a gravitational pull so intense that the rules of the universe begin to change. Long before you even touch the edge, you encounter the strangest funhouse mirror in existence. Because gravity is so strong here, even light is bent into circles. Meaning if you look straight ahead, you might see the back of your own head as your own light travels all the way around the black hole and back to your eyes. This is the photon sphere, the last place where light can still theoretically orbit before being lost forever. But as you get closer, the danger becomes physical and terrifying. You start to feel the noodle effect, or what scientists officially call spaghettification. Because your feet are closer to the center than your head, they feel a much stronger gravitational pull. You are stretched vertically and squeezed horizontally, pulled thinner and thinner until your body is reduced to a stream of hot plasma. Interestingly, this gruesome fate only happens quickly with smaller black holes. If you chose to fall into a supermassive black hole at the center of a galaxy, like Sagittarius A, which is 4 million times the mass of our Sun, the transition might be much smoother, and you could actually survive the initial crossing. So let's assume you took that gentler plunge into a supermassive giant and survived, because the strangest part of the journey is still ahead. Eventually, you reach the true point of no return, the event horizon. Think of this as the trap door of the universe. It is an invisible, one-way boundary that shields a region of space from the rest of the universe forever. Once you cross this line, no information-carrying signals, no objects, and not even light can ever escape. Just beneath this surface, gravity is so strong that space itself seems to be falling inward faster than the speed of light. This is where time starts to do very weird things. To a friend watching from a safe distance, you appear to slow down as you approach the horizon. They would watch you in slow motion, your image becoming redder and dimmer due to gravitational redshift, until you seem to freeze in time just above the edge, eventually fading away into nothingness. But from your perspective, your clock ticks normally. As you look back at the universe you're leaving behind, you would see it speed up into a fast-forwarded blur, eons passing in seconds. You are on a freakish, one-way time travel trip to the future. Once you are inside the event horizon, the very fabric of space and time is so horribly broken that every forward direction you move leads only toward the center. You are now certain to meet a crushing end in the singularity. At the very heart of the black hole lies a single point where all the matter that ever fell in is crushed into an infinitely small space. General relativity predicts that here, the curvature of space-time and the density of matter become infinite. It is like a divide by zero error in the math of the universe, where our current laws of physics simply stop making sense. However, most black holes aren't just sitting still, they are spinning at incredible speeds, sometimes up to 90% of the speed of light. For these rotating black holes, the singularity isn't a point, but a ringularity, a ring-shaped region of infinite density. The rotation is so powerful that it drags space itself along with it, creating a whirlpool called the ergosphere. In this region, it is physically impossible to stay still, no matter how hard you try. The tide of space-time is simply irresistible. Despite everything we've learned, black holes remain the ultimate mystery, because they seem to delete information from the universe. According to the no-hair theorem, a stable black hole has only 3 measurable properties: mass, spin, and electric charge. Everything else, the memory of what the objects were before they fell in, is lost. This creates the information loss paradox, a massive headache for scientists because quantum mechanics says information should never be truly destroyed. There is also the mystery of how black holes die. Thanks to a process called Hawking radiation, we believe black holes slowly evaporate, leaking particles over trillions upon trillions of years. A black hole with the mass of our Sun would take 10 to the 67th power years to evaporate completely, a span so vast it defies imagination. To put it in perspective, our universe is only about 14 billion years old. Stacked against the lifetime of a black hole, the entire history of the cosmos so far is less than a single blink of an eye. Scientists are still debating what really happens at the center. Some theories suggest black holes might be fuzzballs made of quantum strings, or gravastars with cores of dark energy, which would avoid the problem of infinite density altogether. We might never truly know what's inside, because the event horizon guards its secrets well. But that is why we do science, to push into these cosmic no-go zones where the universe hides its most profound truths. For now, black holes remain the most terrifyingly beautiful trapdoors on the grand stage of the cosmos. And if your mind just bent a little out there on the edge of forever, subscribe to Curious Lens. Every week, we journey to another corner of the universe and decode one more of its greatest mysteries.